Hi, my name is Jessica Watson, and today I'm going to be walking through how to solve for the gain of an active low-pass filter using nodal analysis, which is also referred to as Kirchhoff's current law. So first, I wanted to kind of talk a little bit about the significance of active low-pass filters over passive low-pass filters. So passive low-pass filters we're familiar with. This is the structure of them right there. Something that we run into with low-pass filters is that they result in attenuation, even though they effectively filter noise. Attenuation is a reduction of the output signal. Since biomedical signals are already low in amplitude, the passive low-pass filter isn't a great bet. So instead, we're going to use an active low-pass filter, which has an op-amp in the circuit, which allows for amplification, and it also has everything we need to effectively filter the signal. So now that we've determined the significance of an active low-pass filter, let's derive the gain. So to begin with, we have the circuit, and though it's drawn here, it would be much simpler to convert all of the circuit elements into the frequency domain so that we can combine this resistor, RF, and this capacitor, C. So we're going to go ahead and convert all of these elements into the frequency domain. Remember that when converting resistors into the frequency domain, the value remains the same, while when converting capacitors into the frequency domain, the value changes to 1 over JWC. And we have one more resistor up here, which is our RF. Okay, now that we have this, something that we can do pretty easily is combine this impedance and this impedance. We're just going to use an equivalence impedance formula. So we'll do that right down here in green. So our ZEQ is going to be equal to our RF times 1 over JWC divided by RF plus 1 over JWC. And to make that a lot prettier to look at and easier to know what to do with, we're going to move this JWC that's in the fraction in the top down to the bottom so that we get our ZEQ equal to RF over RFJWC plus 1. Okay, so now we're going to go up here and we're going to redraw the circuit yet again into something that's even easier to analyze. So this time we'll have our same op-amp, we'll have the same voltage source, V1, and we'll have our same resistor here, R1. We're going to wire that into the inverting terminal, my bad. And up here, we're just going to have our equivalent impedance, which is going to be our RF over RFJWC plus 1. And then we will finish by drawing our V out over here. So now that we have this, we know what this is. This is just an inverting op-amp. We aren't going to plug it into the formula, but you very well could right at this point. Instead, we are going to do nodal analysis. So our node that we are looking at is going to be here. We only have one, and we're going to call this node A. We're going to define both of our currents as leaving the node. So we'll have a current going this way and a current going this way, as you can see there by the pink arrows. Now, over here, we're going to write out our nodal analysis equation. We will get VA minus V1 divided by R1 plus VA minus V out divided by RF over RFJWC plus 1 is equal to 0. So we've got this equation, which is great, but what we still don't have is a way to solve it because we've still got this VA that we don't have any way of solving. So what we're going to do to fix that is we're going to look at some of this op-amp principles here. So we've got this inverting op-amp. We know what to do with that. We've analyzed this plenty before. So by this point, we know that in an ideal op-amp, the voltage going into the positive terminal and into the negative terminal has to be the same. So here we know our positive terminal voltage, which is 0. So that means that our negative terminal voltage must be the same thing, which is also 0. So we can take our VA and set it equal to 0, just because of that grounded positive terminal. And that makes our analysis a lot easier. So what I'm going to do next is I'm going to move V out over to the other side, so move this whole turn over to that side. So we'll have V1 over R1 or negative V1 over R1 equals V out over RF divided by RFJWC plus 1. And now, to solve this, we will get our V out equals, just by multiplying by this equivalent impedance here that we've solved for, our V out equals negative V1 divided by R1 times RF over RFJWC plus 1. And now, finally, we can move our V1 over to this side. So we're going to divide by V1 because we know that the gain is defined as V out divided by V in. So our gain, which I'm going to write in blue and write it really big because this is our final answer, will be V out over V1 equals negative RF over R1 times 1 over 1 plus RF J omega C. And there you go. This is the gain of an active low-pass filter. So, how do we know that this answer is actually right? All right, if you wanted to be really, really extra and have a little bit of fun with this, we could rewrite this such that it also equaled RF over R1 times 1 over 1 plus JW divided by 1 over, or divided by our cutoff frequency, WC. And how we know we can do that is we know that the cutoff frequency for the low-pass filter is just 1 over RFC, and if that's, just do some basic algebra and get that. But this is how you put it in terms of a cutoff frequency. And we know that this answer is correct because when we look at this, at omega is higher than the cutoff frequency, we can see that our gain is going to start to reduce because you're going to get a value in the denominator that's higher than that in the numerator. So you won't have as much gain and it's going to start going down. So all in all, thank you so much for watching this. I really appreciate it and I hope this helped you some. Thank you.